right? To the degree that separation even exists, and we'll get into that, right? Okay, so that's how I'm building it up. So what I do is I say, okay, well, the set that contains 0 is equivalent to, and we're going to symbolize it by 1, okay? So equivalent to, equal to, similar concept, right? So the set that contains 0 is symbolized by 1. So basically, 0 is to numbers as a letter is to words, okay? It's kind of like what makes up numbers, right? And so what we did is we tried to build mathematics up in this way, right? And then here's the next number, okay? The next number is 0, comma, the set that contains 0, those parentheses, and that is symbolized. So numbers are symbols for things, okay? So you see how I build up 2? That's 2 different elements there. That's 1 element, 2 elements, and both are contained in a set. I symbolize it by 2, okay? So, and then I build up 3, 4, 5, and this is the kind of unbiased articulation that I use to build up mathematics. And what happens is I can start proving, if you will, and by proving, I mean that kind of, most of us got a glimpse of it in geometry in high school where we kind of proved stuff with words and ideas, right? There was a little bit of proving. That's the kind of proving I'm talking about, where you prove things with ideas and symbols, shared symbology, right? And so with this right here, this unbiased building block, I build up mathematics, and I can prove the algebras, and I can prove the calculuses, and I can start to prove all these complex mathematics, right? But there starts to be a conundrum. Things start being provable but unprovable. I'm making a little video. What are you doing? What you need? What do you got going on?
Nothing.
Okay. You out of class? It's my gray matter upgrade partner. Come this way a little bit. And then down. Hi! Alright, yeah, I'm probably leaving after this. Are we having a meeting today? I thought you said like a 4 or 4:30.
It's raining.
So you're not
My
going to
mom
call at all?
I kind of want to take a nap.
Okay.
But
Well, whatever.
it's important to me too, though.
It's whatever. I'll be here at 4 regardless.
Yes.
So.
I may be here.
Okay. Alright. Later, man.
Friday.
Yeah, no biggie. Yeah, we can play at the house or something. Cool. Bye.
Bye.
Thank you for allowing that. Okay. Alright, so the mathematics become provable but not provable, right? And I'm not going to get into it. Number one, because it's not as important to me, the specifics of it. And number two, if you want to check it out, go ask someone who's more versed in mathematics than me. But what happened is building mathematics in this way became provable but not provable, right? Everything was a conundrum. And to clear this up, right, what they had to do is say there is an ultimate set from which you pull 0 and x. And I forget the correct notation, but and it's been a minute since I've worked with higher order mathematics, specifics, right? I'm always working with the ideas and the parables, right? So first you say there's a universal set that contains everything, from which everything, every idea, every articulation comes from. And all you need to pull from it is a building block of the idea of 0, right? And it's not nothing per se, but it is a constant, okay? And so you pull the constant known and a constant unknown, right? And I'm gonna get into this, and for me these are all symbols for reality, okay? So there's an ultimate set from which you can pull a building block that you can't really articulate, but you can symbolize, and an inherent unknowability, right? So that's the first thing in mathematics that got me, right? I was like, okay, well, not the first thing, but It's the first one I'm sharing because it builds up mathematics, right? And the next one was the idea of infinity, okay? 0, 1, 2, 3, 4 to infinity, right? Well, we can look at infinity a couple different ways, okay? At first, you can have the set that contains 0, 1, 2, 3, dot, dot, dot. That's a certain order of infinity. And then you can have the set that contains 0, 1, comma, negative 1, 2, comma, negative 2, dot, 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 dot. See how that's 0 to infinity, and this one is 0 to infinity, but it goes in two different directions, right? So it's got like twice the perceivable parts, right? This one eventually you just say, okay, to infinity. And these, you can get to similar perceivable parts, but double of them, basically, and they go to infinity, right? Well, not even double, but we'll get into that. So that's a certain order of infinity. And then you got 0, comma, 1 to the 1, comma, 2 to the 2, comma, 3 to the 3, comma, 4 to the 4, dot, 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 dot. See how that's set right there? 1 to the 1, 2 to the 2. That goes to infinity, but even quicker in a sense, or it's got a higher order of infinity. And the reason we say it's got a higher order of infinity is because you can use these sets to, they have different modalities and they do different things in mathematics. Like this kind of, the 0, 1, 2, 3 has a certain properties to it, and then 1 to the 1, 2 to the 2, to that set that contains all that has different properties to it, right? In mathematics, we try to ask ourselves, we say, okay, well, or like prime numbers, you know, 1, 2, 3, 5, 7, 11, 13, 17, 19, 23, 27, 29, 31, but anyway, right, prime numbers, they actually go to infinity. There's an infinite amount of prime numbers, right? So what we try to do is say, what is the highest order of infinity, right? What is the highest order of infinity? And we can prove mathematically that there is no highest order of infinity. It only gets infinitely higher, okay? So for me, what that meant is, even if all you had was the worst of the worst, and it was just horrible, that was still more than enough to be put into an infinite, or to create, or to be a part of an infinite reality, right? Because there is no highest order of infinity, it only gets infinitely higher. So there's always something that can be done to convert something into an infinite nature, okay? So that was another thing in mathematics that really struck me, right? And then this last thing I'll talk about when it comes to mathematics kind of brings it together a little bit, or articulates the same thing but in a little bit different way. It's called Gödel's theorem, incompleteness theorem, and it says that once you have a certain amount of rules, theorems, or laws that articulate a certain idea or set of, or like algebra or me or any idea, once you have a certain amount of articulation on it, right, inherently there will be a truth outside of these principles and basics. So what I mean is the basics will be able to articulate a truth outside of the provable truths within the known rules or the known ideas, right? But won't be able to fully prove it. So there'll be a truth that you'll get a glimpse of, but you can't fully prove. And the only way that you'll ever be able to fully articulate it is to completely re-examine, reconvert, and reevaluate and change up the basis of the whole thing, right?